Hello everyone, I'm Masaya Sato of Open University Japan. Today, I'd like to talk about virtual machine monitor-based hiding method for access to debug registers. This is the outline of today's my presentation. First, I'll introduce background and our assumed monitoring method. Virtualization is the basis of the cloud computing. A virtual machine monitor, we call this as VMM, is critical to virtual machine systems because it monitors and intermediate VMs. A VMM is also used for security monitoring basis for guest operating systems. We call this as guest OSes. Due to this, VMM-based monitoring methods are proposed. We call this as monitoring method. The figure shows how a VMM monitors programs on a VM. Some monitor implemented as a VMM and it monitors processes on a virtual machine, and others also monitor guest OSes. In some monitoring methods, breakpoints are used to monitor behavior of programs on a VM. However, breakpoints can be detected or disabled. A program can detect a software breakpoint by reading its memory. A program can also detect a hardware breakpoint by reading a debug register. In addition, malware can override the debug register, and a monitoring method may be ineffective because the method cannot detect behavior based on the breakpoint. Some researchers propose solution for software breakpoints. However, to the best of our knowledge, protection of hardware breakpoints is not proposed. To overcome the problems, we proposed a hiding method for reading or writing of debug registers. A method monitors reading from a debug register and then hides the actual value. A method also monitors writing to a debug register and disguises as if the write succeeded. Thanks to reviewers, we found the BBM BMM's hardware breakpoint manager that solves the stated problem, focusing on hardware breakpoint. The difference between the hardware breakpoint manager and our proposed method is that we avoid emulation to reduce processing by the BMM, and we analyze performance overhead. This slide shows the contribution in our paper. We propose a method to prevent the detection of or invalidation of hardware breakpoints for a VMM-based monitoring method. Reading and writing of debug registers are disguised as though the malware successfully performs these operations. We also present the performance overheads incurred by our proposed method. This slide shows the overview of a monitoring method of guest OSes using hardware breakpoints. The figure shows the overview of VMM-based monitoring method. We assume that the monitoring method monitors behavior of a process on the VM. First, the VMM sets the address of a guest OS to monitor a hardware breakpoint using debug register. Next, a breakpoint exception occurs just before the instruction of the address is executed on the guest OS. Finally, the VMM receives the debug exception and corrects information for the program on the guest OS. Hardware breakpoints is a function provided by the Intel CPU for debugging. Hardware breakpoints are set using debug registers. When the instruction on the address contained in debug registers is about to execute, a debug exception occurs. On the hardware virtualized VM using Intel VT, a mode transition to a VMM, we call this as VM exit, occurs, triggered by the debug exception. Here, only when the exception bitmap managed by the VMM, it is included in VMCS, was programmed to cause VM exits on debug exceptions. Debug exception cause VM exit. So the monitoring method monitors the execution of the guest OS from the VMM. The VMM-based monitoring method has these two problems. The first problem is that the malware can detect the monitoring method's processing. Malware can detect a hardware breakpoint, then the malware can change their behavior to avoid analysis by the monitoring method. In that case, malware analysts cannot monitor the behavior of the malware. The second problem is that a malware can invalidate the monitoring method by overwriting the value of debug registers. Because debug registers are accessible from programs on the VM, the monitoring method is disabled by modifying the value of a debug register. To continue monitoring the programs on the VM, we must solve these problems. Before I introduce the solution, I'd like to show assumption and threat model. We assume malware that run on user and kernel modes on the VM, and they can insert code that reads or writes to a debug register. In addition, the malware may try to our proposed method to continue discovering or invalidating VMM-based monitoring method. These malware activities are beyond the scope of our paper. Anti-debugging using VM detection. It is a common method of evasion technique. And some malware changes their behavior if a virtualized environment is detected. And some malware attacks VMM by exploiting vulnerabilities of VMMs. These attacks are not the focus of our paper. Next, I'd like to talk about the overview of our proposed method. We propose a method for hiding the existence of the monitoring method by making it appear as if programs on the VM can read from or write to debug registers. We show some details for case of reading debug registers from our processes on the VM. When the process tries to read the value of a debug register, the VMM detects reading from a debug register and then sets the requested value to the debug register. Here, previously set VMM set value is saved in the region managed by the VMM. After that, the VMM returns the processing to the VM to continue the processing of the VM. After the processing returned to the VM tried to read the value again, and it succeeded. At this point, the process reads the value the store was previously set, so the process has no doubt about the value. After the reading, a VM exit occurs, and the VMM detects it as the end of reading from the debug register. Then the VMM restores the VMM set value to the debug register and returns the processing to the VM. Finally, the process resumes its processing as if the process can read the required value. However, the actual value is not what they want to read, but the VM-based monitoring method set. So the monitoring method can continue monitoring of programs on a VM using hardware breakpoints. This is the basic idea of a proposed method. From the next slide, I'd like to introduce implementation. To set the proposed method, we must have some preparation. This figure shows the preparation for the proposed method. Here, we assume that the preparation steps are applied just after the monitoring method is made available. At first, the proposal method stores the value of debug registers as a guest OS set value. Then, turn on the detection of reading from or writing to debug registers. This implies that access to debug registers causes a VM exit. The detection of reading from or writing to debug registers is implemented by moved or exiting of Intel CPUs. MoveDR is managed by VM execution control, which controls triggers for VM exits. If field is enabled, a VM exit occurs just before the program accesses a debug register in the running mode for the guest OS. This is VMX non-root mode. With this feature, the VMM can detect a VM's access to a debug register. Next, I'll introduce the processing of the proposal method when handling reading of debug registers. The flow shows the steps when the program tries to read the value of a debug register. First, the VMM detects reading from a debug register and saves the current value of the debug register. After that, stores guest OS set value to the debug register and enable detection of end of reading from debug registers. This step is performed by enabling single-stepping execution. And after that, disable detection of reading from debug registers and return the processing to the program on the guest OS. And after the program on the guest OS continued and tried to reading from the debug register, the VMM detects the end of reading from the debug register. Then the VMM restores the VMM set value to the debug register and disables the detection of completion of reading from debug registers. And finally, re-enable detection of reading from a debug register and return the processing to the program on the guest OS. With this flow, the proposal method disguises the program on the VM as if it can read the actual value, but the actual value is restored after the read. Next slide shows the flow of writing, but it's almost the same, so I skipped this slide. We evaluated the proposal method from the viewpoint of performance. We measure the performance overhead incurred by the proposal method. The table shows the environment for evaluation. We allocated one vCPU to each VM and 1 GB memory to the measurement VM. And we use Zen as a VMM and Debian 7.4 as guest OSes. The figure shows the performance for reading or writing of debug registers for 1,000 times. The left side shows the performance of read and the right side shows that of write. Black bar is the time without the proposal method and the gray bar is the time with the proposal method. The overhead incurred by our method is about 3.574 milliseconds for on reading and 3.571 milliseconds for writing. One reason the overhead occurs is VM exits, owing to reading from or writing to debug registers. No VM exit occurs if our method is not applied. However, two VM exits occur with our proposal method. So the main cause of the overhead is considered as VM exits with the proposal method. By comparing the overhead in reading and writing, the overhead for reading is more significant than that of writing. This is due to the number of instances of writing to a debug register. And even though the overhead is considerable, application mainly affected by the proposal method is debugger. We guess that the overhead does not affect the performance of other operations on the guest OS, so it has an insignificant effect on the performance of the VM. Next, I'll introduce related work. There are two regions related to our proposal method. The first one is anti-evasion on virtualized environment. and the other is anti-evasion techniques not related to virtualization. Because of time, I'll skip this slide. In summary, I'd like to conclude my presentation. We have proposed a hiding method for the reading or writing of debug registers. The proposed method disguises reading or writing of debug registers from a program on a VM as if it is successful, even though the register's actual content is not changed. We also showed the evaluation results. The evaluation results showed overhead from reading from or writing to a debug register on VM. We analyze the main cause of the overhead and compare the overhead in reading and writing. In our future work, we plan to include a more practical evaluation using applications. Thank you for listening.